Hello friends! In this video we will do two main things. First, we will break down how CLIP, Contrastive Language and Image Pretraining works, including its architecture, learning objective and why it's such a clever idea. And second, we will implement it in Python with the dummy image and text encoders and a toy dataset so you can get a feeling of how CLIP works. Cool part is that CLIP is built on a contrastive learning. And that wasn't a new idea when CLIP came out. So the novelty wasn't in the contrastive learning itself, but how authors used it. CLIP teaches models to pull semantically related samples close and push irrelevant ones apart. The trick here is that these samples come from different modalities, images, and text. And the model needs to learn a shared embedding space where, let's say, an image of a lion lives close to the word lion. As you know, one of the biggest problems in deep learning is labeling data. It's expensive, manual, and doesn't scale well. But language and images exist everywhere on the internet. Therefore, instead of human-labeled approach, CLIP uses natural language as a free supervision. Authors scraped image caption pairs from the web and created a huge dataset like they did for ChatGPT. The architecture is simple, modular, and honestly, it's brilliant. You start with a batch of n image text pairs. CLIP considers all possible n combinations in the batch and learns to guess which of these image text pairs actually belong together. So we run all images through one encoder, all text through another, like two separate models. We get embeddings for each modality, but embeddings live in different spaces initially. Therefore, we add a linear projection to bring both into a shared space. The multimodal magic happens here. Then comes the key step, similarity. We normalize the embeddings using L2, so vectors have a unit length. Then compute dot products, which give us cosine similarity. What we get is a matrix where each element tells you how similar an image is to a caption. On the diagonal, the true pairs. Now, we apply Softmax to turn similarities into probabilities, but we want the correct image text pair to have the highest probability. Therefore, we need to use a loss function. And we use a cross-entropy loss, classic choice when comparing predicted distributions to real ones. Here is a clever twist. We don't just compute softmax row-wise, image and text, but we also computed column-wise, text image. Therefore, we compute two losses and then we take the average of them to get the final one. This symmetry strengthens the model's learning from both directions. Now, backpropagation. What gets updated during training? Everything. The image encoder, the text encoder, the projection layers, and even temperature parameter. Let's talk about that. CLIP uses scaled cosine similarity logits in its contrastive loss with the temperature parameter T. Why? Because temperature controls how confident the softmax is. Lower temperature, sharper distribution, more confident predictions. But tuning temperature manually is annoying. Therefore, the authors let the model learn it by optimizing logarithm of 1 over tau directly during training. As a next step, we build a training loop in a Python to understand how CLIP works. As I said previously, we are using dummy image and text encoders. But anyways, I created these abstract classes because every implementation should have this interface like initialization with a embedding dimension. Like for image it's di, for text it's dt, and an encode method that takes image and encodes it. So the dummy encoder it's very simple. It's just a randomly initialized matrix of the size, a number of samples in the batch times the embedding dimension. Same for text encoder. These are the functions that we are going to implement together, which is L2 normalization, Softmax, and cross-entropy, as well as clip cross-entropy. So let's see training loop now. For this, I just created a toy dataset I and T, I for images, T for text, just for understanding, but we don't actually use it. So the dataset consists of 4 images and 4 texts, and text 1 is a caption for image 1. And we will go through it batch by batch, which is in this case just the size of 2. And yeah, just randomly created sizes for image embedding dimension, for text, and DE is a shared embedding space. So I use pretty much the same notations as used in this pseudocode. Training loop is straightforward too, so let's go here line by line together. We create image encoder, text encoder, and then clip objects and pass embedding dimensions like DI, DT, and DE, and image encoder and text encoder to initialize it. We then initialize parameters like WI and WT that create a shared multimodal embedding space, and we move the model to device. And we also initialize optimizer, which is in many cases Adam that works efficiently and does its magic. And yeah, we then train the model batch by batch, and yeah, we just run the clips forward method, passing it a batch of images and text, and it returns us logit image and logit text. We then pass these logits to the calculate clip cross entropy loss function we are going to implement together. As for Softmax, let's recap how it's calculated. So we have logits matrix where each element corresponds to the cosine distance between image and text vector. And Softmax will turn these logits into probabilities. So the magnitude of each of the vector for per every sample is gonna have magnitude of have the sum of will sum to 1. And the formula for this is the following. In the numerator, we have exponential of the logits, and we divide it by the sum of these exponentials for every sample, so per row. And let's do it. So we first calculate the logits exponential, and we do it using torch exponential logits. And then we return logits exponential, and we divide it by logits exponential sum for every row, dimension 1. And we need to keep dimension in order to prevent output tensor to change its shape. However, imagine when logits become really large and exponentials can just explode. So the trick we can use here is actually use shifted logits. What we can do, we can subtract the maximum of the vector. And so it's going to be something like logits maximum dimension 1 and keep dimension is true values. As for cross entropy, so again, we have a softmax matrix where each element is a probability, and we want to compare it to the real distribution. We want the values for the true image and text pairs to be as high as possible. So we use a cross entropy that is calculated as a logarithm of the true pair probability. And in this case, true image and text pairs live along the diagonal. So we need to calculate the logarithm for every diagonal value in the matrix and then take the mean of it. So when we implement functions for torch, we should prefer parallelization. So it's going to be efficient on GPU. And finally, for clip, it's also easy because, yeah, we need to calculate cross-entropy for images and for text separately, so symmetric loss function, and then we take the average of these two. So we passed all the tests, which is great. However, there is one test that we are gonna not fail exactly, but you can see that for this logits matrix, our cross-entropy function returns infinity, right? So it's gonna just break our numerical stability. And this is coming from the zero value, because when we take the logarithm of zero, it's infinity, right? So we need something better. And the trick here that we can do is to actually simplify this equation of cross-entropy into second one. And let's understand together how we do it. So we first need to remember that logarithm of x over y is equal to logarithm of x minus logarithm of y. So, and also logarithm of exponential of x is equal to x. And that's why our numerator here turns into just logits minus logits. And then our denominator is as simple as just logarithm of this denominator. I suggest us to do it by ourselves just for educational purposes to understand the concept of softmax and cross-entropy better. However, of course, there is a torch function, torch and then functional cross-entropy that we can just use, and it has much more efficient and numerically stable implementation. So let's go to the exciting part, implementing the clip model, and we start with the initialization of it. So the easy part is to do the self image encoder to the image encoder, self text encoder to the text encoder, and then we need to initialize parameters. So self wi, self wt, and these are our projection matrices, and self logit scale, which is basically our temperature parameter. And for this, we're going to use torch parameter class. So next part is initialize parameters with actual values. So our parameters, we're gonna initialize our self wi and self wt, and we're gonna use torch and initialize module, and it says all the functions in this module are intended to be used to initialize neural network parameters, right? And let's do it together. And init normal, and we pass it our parameters self wi and mean. We set mean to 0 and standard deviation to 0.02. Again, copy paste for wt and done. So the last method we need to implement for our clip model is exciting one, forwards. So we're gonna follow the pseudocode in the clip paper. And then first thing we need to do is to run image encoder and text encoder to get the image and text embeddings. So if is equal to self image encoder encode I, repeat for text, next part is to calculate the dot product between the image encoding and the projection matrix and do the same for text and follow it by the normalization to unit norm. I e is equal to L2 norm, a function that we created earlier, torch, and we use tensor dot function to perform the matrix multiplication between if and self wi, and we need to pass dimensions, which is 1, and we also calculate the projection for te, so tf wt, and finally we calculate logits like we do the matrix multiplication of ie at te, but transpose and multiply by the logit scale exponential of it. Because here in init we defined it as a logarithm for numerical stability, but we actually need to divide by temperature parameter, which is 0.07. That's why we need to take the exponential, because the exponential of the logarithm of x is known is equal to x. And now we also need logits for text, because this is logits for images, meaning that in every row contains information about how image is close to every text in a batch, and we need to do the same for symmetrical reasons for the text to help model to learn these directions better. And we just take the logits image and transpose it, and yeah, we just return logits image logits text. So let's run the kernel from the start and see if our training loop is working. Yay, so it's working and our little prototype for clip is ready. In the next series, as I said, we're going to plug in actual image and text encoders and do the training on real dataset.